Okay, so today we're going to put it all together, and this is the thing that was like a lightning bolt to me when I was taking physical chemistry and I got to graduate school. I mean, I'd learned in PChem point groups, and we had labeled molecules with point groups, and in inorganic, they kind of use some of those point group labels, E2, G or T2G and EG labels for the splitting of the d orbitals and so on in an octahedral character table, but they didn't really connect it to the character table. They just labeled those energy levels, and they didn't really know what EG and T2G were, or what or T1U or whatever the different labels were. And we never did selection rules. We never calculated transition dipole moment integrals. So when I first saw that in graduate school, it was really like a lightning bolt. It explained everything as to why symmetry was important. And that's why this course is so focused on symmetry. So y'all are really getting, I would say, it's not a new perspective. I learned it from my advisor, but it's so sad that it's not taught everywhere. Like, what is the point of a point group? Well, today we're going to learn what the point of a point group is. It really allows us to understand the spectroscopy and the selection rules. So those of you who've had me here for undergrad, it's been beat into your head, but at other schools it's not even talked about. And so that's what's surprising to me, is that so many schools will teach symmetry, and even textbooks like Atkins textbook, which is sort of the market share, the largest textbook in PChem, and they introduce symmetry, but then they never use it. They never do the selection rules calculated with a transition dipole moment integral. So that's why when you look at the Atkins book and you're in my PChem class and you wonder, where are we? Okay, we're off the book because we're trying to use the symmetry that we've learned to show why it's important. And so today we're going to do that. We're going to look at molecular symmetry and the transition dipole moment integrals. And this is really the point of using point group symmetry. So this is way down the table. We've talked about the need for symmetry. We start with that Lewis dot structure. We get a 3D shape, and then we get the point group, and now we have the character table. We just went through all of the MOs and the vibrational motions and assigning symmetries to those. Now, it's more than just fun, okay? We're not just doing those wave function symmetries because we can. Once we get down to the wave function symmetries, now we can see how light can interact with those wave functions. So this is the point of spectroscopy. How does light interact with matter? Matter can vibrate, matter can have electron clouds, and this tells us how light interacts with those things. Is once we know the symmetries of those things, we can know when light will interact with this wave function and not that one. So that comes through the character tables and the direct product tables, and that allows us to do selection rules for spectroscopy. Can a photon of light interact with these two wave functions to cause absorption of energy or emission of energy or a scattering of energy? So we have all of those different kinds of phenomena, and we can look at the wave functions and know this is possible and this is not possible. So we have the symmetry, not just of individual wave functions, but the total wave function, which is just, I put this in here just as a reminder, or if you haven't heard it before, to tell you that it's the electronic wave function times the vibrational wave function times the rotation times the nuclear. So it's the product of all of those wave functions. And so we have a lot of products of functions, and we can follow those symmetries using the direct products of those rows of the character tables. Just as an aside, so the total wave function, so psi total is equal to the product of individual wave functions, okay? So the big P, big pi here is a product function. The total energy is equal to the sum of all the energies. Okay, so it's just something to keep in mind. When you're doing energies, we have the sum of all of those energies. So you have the electronic energy plus the vibrational energy plus the rotational energy plus if there's translational energy and so on. Whereas the wave functions, it's the product of all of those. Wave function 1 times wave function 2 times wave function 3. And if we bring light in there, there's the wave function for light, or symmetry of light, and we can put that into this product as well. We're going to have these direct product tables related to the point groups, and we're going to use those. So we have this, this is really the main point here, that the intensity in the transition going from N to N prime. So we have N and N prime. The intensity of this transition right here is proportional to this transition dipole moment integral squared. So this is the wave function of N. This is the wave function of N prime. This represents light. If we have direct absorption, it's the dipole moment. Operator. The ER or R? I always can't remember. And then we end up with this this integral over all space of these three functions times each other. In Dirac notation, we just use those angle brackets. So I'm just showing you explicitly that's an integral over all space. D tau means all space. And then we need to use symmetry to know when this integral is 0. So an integral of an odd function is 0. An integral of an even function is non-zero. And this will tell us when and where we're going to have peaks. So if the result of this direct product of these three functions, the symmetries of these three functions, does not contain the totally symmetric irreducible representation, which is that top row, then it is equal to 0. And we say that it's forbidden by symmetry. So that intensity will be 0 because this transition dipole moment integral is 0. And we will say this transition's forbidden by symmetry. Now think about what that means. The light is coming in, it's hitting the molecule, atom, ion, whatever. So light has hit that object. And the energy of that photon of light matches the energy difference between these two levels. So you know, this photon of light comes in and hits that molecule, and it has the energy that matches. So it's exactly the correct wavelength for that transition, but the symmetry won't let it happen. So that light just goes right through. No absorption. So that's what I want you to think about. We have a spectrum. We have differences in energy levels, and when we take a spectrum, we might start out scanning the spectrum, and we're scanning the wavelengths of incident light, and it's like this arrow is getting longer and longer and longer, right? And we go past a transition, and you know, when we're right at the correct wavelength, we should be able to make that transition happen. But if the symmetry doesn't work, that light will go right through, even though there's an energy level there. And so how would you understand that? It's not just energetics, it's also symmetry. So it's not just if there's an arrow long enough that gets you to that energy level, you'll have absorption. If the symmetry doesn't work out, it's forbidden by symmetry and the light will go right through it. Okay. So that's what we're looking for. So I just want to repeat that. If the symmetry doesn't work out, then that transition is forbidden by symmetry. And what does work out mean? It means that the product of all three of those functions, or more, if it's a combination band or something like that, then the result has to contain the top row. And we'll understand what that means here in a little bit. We're going to do some of these transition dipole moment integrals. So to summarize, we use that Vesper theory to estimate the geometry. Then we find the point group. Then we use the Millikan symmetry of the wave functions, like the projection operator or inspection, to determine the symmetry of that wave function. You know, we could compare it to the x-axis or the y-axis. If it's that pattern of x plus minus, then we have the x times z or x times y. And then we select the symmetry of the spectroscopic interaction. So for direct absorption or emission, we're going to pretend that the molecule is fixed in space and we can send polarized light that's polarized in the x direction, or polarized in the y direction, or polarized in the z direction. So we're going to use those three main axes, which are really our lab axes. You know, we can adjust the polarizers and send x-polarized light into our system. And even though we can't really fix an atom in space and hold it in position to where the orbitals line up, we can't really detect one atom. And so we're going to have an ensemble of atoms, and some of those will have those orbitals lined up with the p orbital right along the x-axis and so on. So it's really not important to the directions of the atoms. Some of them, if it's allowed, will be aligned just right for light to absorb, you know, along the x-axis with x-polarized light, or y-polarized light, or z-polarized light. So when we're talking about these symmetry of the spectroscopic interaction here, the X, Y, and Z are for direct absorption and emission. Now, what are the other types of spectroscopic interactions that we deal with? Scattering. So we could have Raman scattering or Rayleigh scattering. And so these are some second order combination of the X, Y, and Z axes. One way I think of this is if our molecule is here, let's say along the X, Y, and Z axis. For scattering, we have a two-photon process, right? And so let's just think of it as a photon coming in on the x-axis and leaving on the x-axis would be x squared, okay? A photon coming in on the x-axis and leaving on the z-axis would be xz, right? You can think of it that way. You could also, if you really wanted to dig into the patterns and so on, think of a wave that's polarized in the y direction interacting with a wave polarized in the z direction, and you would have this pattern of plus minus plus minus, and so that would be a YZ interaction with that atom, and that would interact with things like the d orbitals that have that same plus minus plus minus. So, but in general, since the scattering process is a two-photon process, you have second-order interactions, xz or x squared or y squared. Or sometimes in a different character table, those symmetries will take the form of x squared plus y squared plus z squared, sort of a spherical interaction, or they might take a x squared minus y squared. And so any of those second-order ones would be the types of interactions you'd have for scattering, either Raman or Rayleigh. And then we use that direct product table to determine the symmetry of this transition dipole moment integral. And for direct absorption, technically, it's a dipole moment integral. For scattering, it's a polarizability moment. So it's not a dipole because you have essentially two axes, you have two dipoles, and so it would be the second order interaction of two dipoles. And so let's do this flashback to the particle in a 1D box for continuity. This was the 6 pages of math that we reduced to a Post-it note. And so we only have one axis. We have E and I symmetry elements, the smallest, almost the smallest character table. C1 is smaller, but this is a 2-row, 2-column character table. And we have those wave functions labeled even and odd, AG and AU. And here's our transition dipole moment integral. We want to know, is this an allowed transition using the X polarized light? So we come over here and we need to put in our symmetries for n equals 1 to n equals 2. And so here's our symmetries. So for n equals 1, down here we have AG. For n equals 2, we go over here, this is AU. And for our light, we come up here, we're just going to use X polarized light since we have the X axis here. So our light's polarized along the X axis. Okay. So it's really not coming in on the X axis, it's polarized on the X axis, and that sets up that dipole moment on the X axis. And that X axis is AU. So this is the interaction of our light right here. So The light is in the middle. Does everybody see the interaction? Lower state wave function, light in the middle, upper state wave function, and then we do the direct product tables. So this is a character table. So this character table is there. Direct product table is here. Notice how they look different. Direct product table does not have ones and zeros in here, or ones and minus ones. The direct product table is the products of all of these different symmetry elements. Character table has the characters in it and these other axes and stuff like that. So don't get those confused.
So just whether it's even or odd is what we're doing. We'll plan them together.
Exactly, yeah. So even times even is even and odd times even is odd, yeah. So we're going to take these two at a time. And so you just come up here. Notice how I've got AG times AU, and I do AG times AU, and I get right here. I say, wait, there's a blank square there. Well, this is a symmetric table, so just go over here. This AG times that AU gives us this one. Okay, so people are lazy, and chemists and printers are people. Therefore, they only print half the table typically. Okay, just the top triangle of this table. So don't be bothered by that. It's just the way it is. Okay. And so AG times AU is AU. And then we have another pair. We do them pairwise. AU times AU is AG. So this AG here, we go to the character table. I'm going to go way around here. And that's the top row. Therefore, this is not equal to 0. Okay. Because this right here is the top row, then we have this non-zero result of our integral. And therefore, our 1 to 2 transition is allowed in this situation, okay, with X-polarized light. Okay, so any questions on that?
In the AU XYZ, there's a figure for IR spectrum.
Yes, and so for IR, we're going to get into IRs as well with molecules and our wave functions, yeah. And then we'll do rotation and we'll do visible light too. Okay. So can we do this in general? This was for 1 to 2. Okay, so let's think about it in general terms. It says essentially by symmetry, any AG can connect to an AU. And if we were to swap these, if we were going from an AU to an AG, it would be the same symmetry workout, okay? And so we can generalize. Our selection rules now will connect any AG to an AU. So I can go from this one to there, so 1 to 2, but I could go to the next AU up here, which is 1 to 3, okay? The fourth level, let's see, 1 to 4. It's 4. Yeah, let me just erase that. Something didn't sound right. So 1 to 4. Okay, then 5 is going to be AG, and then 6 is AU. Okay, so I could go up to 6. So 1 to 6. So that's a delta N equals 5. This is delta N equals 3. This is delta N equals 1. So 1, 3, 5, and the symmetries alternate. So it's going to be 9, 7, 9, it's 11. And so we can generalize. And now here are the selection rules for our particle in a 1D box. Notice the selection rules are the allowed transitions. So that's by definition. When we talk about selection rules, we're labeling the allowed transitions. Make sense? Okay. It's a bit of a review. Now let's look at scattering. Okay. So scattering in this particular system, we only have one axis, and so it's x. So scattering will be x squared. And and typically when we're looking at scattering, we want to look at incident light that doesn't match any wavelengths, and so that we have our photons of light that interact with the system in between the energy levels. So this incoming light typically we use lasers because we can select that incoming light, and we pick a laser wavelength that doesn't match any of our other levels. There is a way to do, it's called resonance Raman, and you can get some signal enhancement using resonance Raman, but most of the time it's like this, where you have this, what they call virtual level, that's not matching anything in the system. So can light scatter inelastically from 1 to 2? That's the question. So we have 1 to 2 with the x squared operator. We do the symmetries of those, just like on the previous slide. 1 is AG, 2 is AU. We work the direct product table in pairs. AG times AG is AG. AG times AU is AU. And notice AU is not the top row. So our result is AU. Therefore, this is equal to 0. Therefore, 1 to 2 is not allowed or forbidden by symmetry. So light scattering cannot cause this molecule or system to jump from level 1 to level 2. Okay. What can it do? Well, if the final state is AG, then it's allowed. So we have AGs all around, and so that's top row, and that's going to be allowed. So we do have this situation where we can have light interact with this level and that level, and so we could have it jump, and we could have it interact with itself. So it could scatter light. So we could have delta n equals 0, which is Rayleigh scattering, which is shown here, where it comes back down to itself. And we can have Raman scattering, where it goes up to n equals 3. So 1 to 3, delta n equals 2, and then, let's see. Yeah, 1 to 5 would be delta n equals 4, etc. So any questions about this? This is our simple 1D particle in a box system. I want to make sure you're comfortable with it before we get into the more complicated wave functions. Okay. All right, let's dive in. So let's look at rotational motion. So if we observe the energy level diagram for rotational motion, we'll notice something. We'll notice that all of the even quantum numbers are top row. Whatever that molecule is, it's top row. It could be A1, it could be A1G if it's got an inversion center and so on. But all of the even quantum numbers are top row. So you see here J equals 0. Here J equals 0, top row. J equals 2, top row. J equals 4, top row. Okay. And then the odd quantum numbers are the symmetry of the motion. So the odd quantum numbers match the symmetry of the motion. So whatever that motion is. So like in water rotating around the y-axis, you find Ry in that character table, and that's what those odd J values are. So I can't say which symmetry it is. I have to just be generic and say for that molecule, wherever Ry is, that's the symmetry of the odd J values. And so for the ones shown on the right, this is Ry in water. Okay. And so with that setup in our energy level diagram, now we can go to the character table for water and we can see what our selection rules are. So here's our character table, here's our direct product table, here's the rotation around Y. If we find our Y here, then it's B1. So we see that that's B1. Okay. And so the question is, can this rotational mode be excited by direct absorption of light? It's a molecular point group of C2V. So the even quantum numbers are A1. The odd quantum numbers are B1. Wherever Ry is, you find that symmetry. And then here, the others are Rx equals B2 and Rz equals A2. So we have, again, the even quantum numbers. So like J equals 0 is here. J equals 1 is there, and light is here. So we're going to try Z polarized light first. We have the A1 here. And so we put in the symmetries. So A1 times A1. So we do these in pairs. So it gives you A1. So you have this chart here, A1 times A1 gives you A1. And then the next one is B1 times A1. And so we have B1 and A1 here gives us B1. So our result is B1, and that's equal to 0 because it's not the top row. Then if we put in X polarized light, again we have 0, 1, and X. J equals 0 is A1, J equals 1 is RY. We can put in the symmetries for those. X is B1 and RY is B1. So A1 times B1 is B1, and B1 times itself is A1. Notice this diagonal here down this direct product table. Anything times itself will give A1. And later we'll see in threefold symmetry and higher, there may be other things in there with A1, but it's always going to contain A1. Anything times itself will contain A1. And since this is A1, the integral over all space of this function, remember this is an integral, and these are three functions times each other, which would really, for rotation around water and light, it would be ridiculous. In 3 dimensions, a huge integral, way more than 6 pages of calculus. And yet we can know that the integration of over all space of this really complex function is going to be non-zero. So this is not equal to 0, therefore allowed. Okay. Now we can generalize. So let's look at this. In rotation, one of those levels, okay, is going to be A1. Okay. Either we're going from 0 to 1, or we might be going from, let's say, emission. We might be going from 1 to 0. So this one is going to be A1. And so if RY is B1, and we need something to match B1, then X is going to match that. If we look here, we see RY and X are on the same row. We know that rotation around Y, we find rotation around Y, and we know that X polarized light is right there with it. And so that's going to be allowed. What about rotation around Z? Nothing. There is no X, Y, or Z on that row. So rotation around Z cannot be excited by direct absorption of light. But our rotation around X can be excited by Y polarized light. Okay. And that only works because one of the three things here is A1. So you're really only working with two species. One has to match the other. And so that only works for rotation and vibration. Okay, so
would rotation around Z be allowed with scattering?
Yeah, very nice. So what could cause rotation around Z is a two-photon interaction here of XY. So X polarized light hitting that molecule and leaving along the Y polarized direction. It can leave in different directions, but it's polarized in the Y direction. So that rotation around Z can scramble light coming in on the X-axis and sending it out on the Y-axis. So it's sort of that angular momentum is interacting with light and bouncing it off into the Y polarized direction. Let's look at vibration. So vibration also has alternating energy levels. So the even quantum numbers are top row. So V's now, V equals 0 is A1, V equals 2 is A1, 4, 6, etc. And then the odd quantum numbers, so V equals 1, 3, 5, etc., are whatever the symmetry of the motion is. And so when you did your Millikan notations for the vibrational motions with the arrows, those are the symmetries of the odd vibrational quantum numbers. Okay. So in this case, we have this asymmetric stretch for water labeled as B2. And so then let's look, can this vibrational mode be excited by direct absorption of light? Even V's are A1 and the odd V's are B2. And so here's our symmetry setup for the transition dipole moment integral. So we're going from 0 to 1 in the vibration. We have light in the middle. This particular asymmetric stretch has got Y symmetry, which is B2. So we have Z polarized light, which is A1. Times A1 gives A1, but A1 times B2 gives B2. So that's equal to 0. So Z polarized light will not cause this asymmetric stretch. But you can imagine that Y polarized light would, because of Y motion and Y polarized light are going to interact with each other. So Y polarized light is B2, and the Y motion is B2. They interact to give A1, which is not equal to 0, which means it's allowed. And once again, we're pairing those things up. So since one of those levels is A1, the other two have to cancel each other out in terms of their oddness and give us the top row. And so the Z polarization, Z polarized light will excite Z vibrations, X polarized light will excite X vibrations, and Y will excite Y vibrations. And that's why this is called essentially IR, because these are the IR selection rules. You know, if you label your wave functions with X, Y, or Z and their symmetries, then you know that those are going to be IR active. But if you have some motion that's not one of those Cartesian symmetries, then it's not IR active. Okay. We'll see some of those in a second when we get to acetonitrile. So we've done rotational spectroscopy, we've done vibrational spectroscopy. Now let's do electronic spectroscopy, or UV vis. Okay, light interacting with the molecular electron cloud. So in this case, we have the highest occupied molecular orbital on ammonia and the lowest unoccupied molecular orbital on ammonia. And so can the HOMO to LUMO transition occur through direct absorption of light in this situation? And we have Z polarized light in this character table is A1, and XY polarized light is E. And so this is what we need to do. We need to look at the symmetries. Well, we've been given A1 as the highest occupied molecular orbital and A1 as the LUMO. And so the direct product symmetries are pretty easy to set up. We see this as all A1s. We know that one's going to be allowed because A1 times A1 is A1. And so all of those are going to give A1s. But this next one we're concerned about. So we'll look at them individually and give you some time to fill in the blanks. Okay. You can go back to the video if you miss it. Okay, so Z polarized light, sure enough, A1 times A1 times A1. Again, the direct product table, A1 times A1 is always going to be A1. So it's not equal to 0. So Z polarized light could cause this transition to occur. What about XY polarized light? It happens to have E. So E times A1 is E, and then E times A1 is E, so therefore it's equal to 0. So XY polarized light will not cause this transition to occur. So it is allowed for Z polarized light, but forbidden for X or Y polarized light. Any questions on this one? Okay. So molecular orbital selection rules are not easy like the rotation and vibration selection rules. Because if you think about it, we have three unknowns in this one. In the vibration, we know that one of those is A1 because we're either going from an even quantum number or to an even quantum number if we have a delta V equals plus or minus 1. Okay. In rotation, we have delta J plus or minus 1. So if we're going up by single jumps, then we're either going from an even to an odd quantum number or odd to an even quantum number. So again, one of those three things is A1. So we just have to match the other two so that the odd character cancels out. So if those others are equal. If it's Rx and Rx, we know it's allowed. If it's X and X in vibration, we know it's allowed. But for the molecular orbitals, we don't have this nice, easy quantum number thing, right? What are the quantum numbers for the molecular orbitals? Have you noticed that? We don't really have them, do we? We have quantum numbers for the atomic orbitals, N, L, M sub L, M sub S. We combine those to make molecular orbitals. We've lost our numbers. They're still quantized, but we don't have any numbers. So there's really no convention that has survived the literature or sort of become a trend in the literature of how to label our molecular orbitals. And if we don't even really have a convention for how to label them, we certainly don't have any convention as to which symmetry goes with which label, right? And so the only way to really label molecular orbitals is with their symmetries. And so you look at those orbitals and you compare them to the character table and you label them by their symmetries, and then you might label them from low to high, 1 through whatever. But again, that's not sort of arrived at the literature. The symmetry labeling of molecular orbitals is the only thing that really can give you a grasp of it. And so we have this set up for the transition dipole moment integral. We don't know what the lower wave molecular orbital is. We don't know what the upper molecular orbital is. And the middle could be X, Y, or Z. So we really have to go in and look at the orbital, compare it to the character table, come up with the symmetry of both the upper and the lower state, and then look to see what X, Y, or Z light would be in terms of that same character table. But I see a lot of people make mistakes when we're doing MO diagrams. They will assume that this is A1, but you can't do that. You cannot assume that either one of these is A1.
So, like on our homework, when we're building the molecular orbitals from the linear combinations.
Yes.
And so we know that they have to be the same to combine.
Wait. Yeah, okay, yeah. In the molecular orbital diagram, they have to be the same atomic orbitals or symmetry-adapted linear combinations to interact with each other and produce molecular orbitals of that same symmetry.
And so we know the symmetry of the molecular ones from that.
Mm-hmm.
And then we can sort of find the limo and all.
Yeah, so let's practice. Let's do some of these. So these are the vibrational modes. So acetonitrile, here's all of the frequencies, A1s and E's, right? And this is not in your notes, but just, these are all the frequencies for acetonitrile. And if you know the symmetry of that vibrational mode is A1, then you know that one of these is A1, the other is the ground state, which is A1. And so in the middle, you just need another A1. And so you know that Z will go in the middle, right? But you also know that Z squared will go in the middle. So this is both Raman and IR active. Because there's a IR piece and there's a Raman piece on that same row, A1. And that's the same for all four of these. So all of these peaks are present in the Raman and the IR. So you can just immediately know that, and you know that it's Z-polarized light in the IR that's going to cause that transition to occur. Okay. Down here, E. Okay, so we've got E in the upper state, A1 in the lower state. And we just need something that's E to cancel with that E and give us an A1. And so XY polarized light is E. And then all of these kind of guys here are E. So it's also going to be Raman or IR active. So X, Y would work, and X y times Y or X times Z, etc. So these are going to be Raman and IR active. All of four of those E's. So acetonitrile has peaks in the Raman and the IR at all these frequencies. It's not centrosymmetric. It doesn't have an inversion center, so we don't have that split, that mutually exclusion of spectra. We just have the same peaks in the IR and the Raman. They'll have slightly different intensities based upon the change in the electron cloud for the scattering or the change in dipole moment for the vibration, but they're all active in the IR and the Raman. Now let's look at ethene. So we finished that ethene MO diagram. Let's look at the HOMO to LUMO transition. So this isn't in your notes, so go ahead and just write here an energy level that's labeled B1U and an energy level that's labeled B2G. And we want to know what polarization of light, if any, will cause that transition. Does everybody understand the problem? We're coming up with the selection rules. Can light even excite the HOMO to LUMO transition in ethene? It's not going to be visible light because this is the extent of the visible light, so it'll be UV light, but it'll still be, a single photon of light. So B2G is here, B1U is there, and we want to know if this is equal or not equal to 0. We need the direct product table. I don't have that on this slide, but let's see. So B1 times B1 is A1, okay? B2 times B2 is A1. B3 times B3 is A1. Okay, so we know those. And this is kind of weird. B1 times B2 is B3. And B1 times B3 is B2. They kind of alternate with each other. Okay. Let me kind of draw this up. Okay. And so if that's the case, what do you think B2 times B3 is?
B1.
Yeah, B1. Okay. Now, where am I using G's? A lot of times the tables will just contain the numbers like this.
Well, it's even and not even.
Yeah, and so U times G equals U, U times U equals G, and G times G equals G. So you have the G and U rules on top of the numbers. And so what we need to do is we need a B1 times something to produce a B2. So when we do this multiplication here, we need B1 times something that will give us a B2. Yeah, B1 times B3 will give us a B2. Okay? And we need a G here. We need a G here. Because we need B2G times B2G to give us A1G. Okay? So this needs to be a what? I heard of both, G and U. Which is it? It needs to be a U. So U times U is G. Okay? And so then this is going to produce now, this one will come down, B2G, and multiply by those together, and that's going to give us A1G, which is top row, which is not equal to 0. So this right here is what we need. Then we come down here and look for B3U. And then we come over here, and it's X polarized light. So we've got it. X polarized light will cause the HOMO to LUMO transition.
But say, like, if we needed AU symmetry, then it would be possible.
No, AU is in top row. So all you got to think of is top row. Yeah. And so then you can do, I mean, I'm going to ask you on the test, I mean, what about the pi to sigma star transition or something, B1U to B3U, and, pick any two, right? But notice how in UV vis and X-ray too, I guess, none of those are A1. They don't have to be, right? In vibration and rotation, one of those three things is A1 or top row. But in UV vis, a lot of people make mistakes. They'll write this thing out and they'll put an A1 there just because they think that's always the case. It's not always the case. It is for vibration, it is for rotation, but not for UV vis. Okay, so that was another main point I want to emphasize today, that for UV vis, you have to explore what the top wave function is and what the bottom wave function is, because those symmetries are not guaranteed. Okay, so you got to know what they are from the energy level diagram.
You would give us the diagram on the.
Yeah, you have to know what those symmetries are. Yeah, you have to know. But now, if I just say this vibration in the character table, like for this particular molecule, you've got vibration, which happens to be the symmetry of Z. Okay, you know, if it's vibrational motion, you know Z polarized light would interact with it, because one of those is top row. So for vibration, it's A1G, and if it's Z vibration wave function, then it's also Z light, because this is A1G. So you need the B1U and B1U and AG, and these two give you A1G times A1G. See? And so that's going to be allowed. So for vibration, it's easy. If it's a Z motion, then you have Z polarized light that will interact with it. If it's an X motion, X polarized light will cause it to absorb. But for HOMO and LUMO, or UV vis, you got to know what those symmetries are, because you got to build out your problem. But this is amazing. We're doing incredibly complex math here, integrals, and knowing whether they're allowed or not with just 3 lines of math. Now, don't leave off the brackets. So you get lazy and just use the symmetries. But when you show those brackets, you're actually showing you're doing an integral, and that integral over all space is not equal to 0 or equal to 0. Okay, so keep all of the math, brackets and equal signs and everything, so that you can show me you know what you're doing. Okay, don't just do the symmetries. Okay, all right, that's a good stopping point.